Okay, so when the input voltages are very small, say less than 0.7 volt, let's say 0.1 volt or zero point 0.2 volts, then the diodes cannot rectify them, right? So the diode rectifies, generally a silicon diode rectifies any voltage which is greater than 0.7 volts, and it doesn't rectify any voltage less than 0.7 volts. So precision rectifiers are used in order to rectify very small input voltages, as in the sine waves. When V peak for a sine wave is too small, when V peak when V peak of a sine wave is smaller than 0.7 volts, then you cannot use silicon diodes to rectify such voltages, right? Silicon diodes cannot rectify such voltages. So therefore, you make use of precision rectifiers in order to rectify small voltages. So now we use something called as super diode for rectification of small voltages. So it's called as super diode. So this circuit is a combination of a diode as well as an amplifier. So it goes like this. So first you have an op amp, right? And then you have a diode which is connected in a feedback configuration. Okay, and here you have a resistor RL across which you're taking the output voltage, and we call this as Vn. So this portion, okay, so this portion is called as a super diode, right? Let me mark that. This portion is called as a super diode. This is called as a super diode. Okay, so now let's see how this works. Now suppose at Vi we have a positive voltage. Now we don't know whether this diode is forward biased or not, and whether we have a feedback path here or not. So therefore, when we have a positive voltage at Vi, since Vi is connected to the non-inverting terminal, the voltage here, so let me call this as Vx, right? So Vx is also positive, right? So this positive voltage forward biases the diode. This positive voltage forward biases the diode. Once this diode is forward biased, now there's a feedback path between the output of the op amp and the input, and this will behave like an voltage follower, right? So once you have a negative feedback here, so the voltage here at this point will be same as that of the input voltage. So the voltage here will now appear at the output V0. So therefore, how does this basically work? If Vi is equal to positive, then D1 is forward biased. So now there is a feedback path established. Feedback path is established. So now this will behave like a voltage follower, and therefore you will have V0 is equal to Vi due to the virtual short. Okay. So now what happens if Vi is negative? If Vi is negative, then what happens to the diode? the diode D is reverse biased. The diode D is reverse biased because if Vi is negative, since you're giving the input to the non-inverting terminal, Vx is also negative, and this reverse biases the diode. Since the diode is reverse biased, now there will be no current flowing through RL, and therefore V0 will be 0, right? So there's no feedback path established. So it looks something like this. So it looks something like this. So now this will be an open circuit. This will be an open circuit when Vi is negative. So now see this, since this is an open circuit, there will be no current through RL. When there is no current through RL, V0 will be V0 will be equal to 0. Right? So the concept of virtual short doesn't hold good here because you have an open circuit, and therefore V0 will be equal to 0. So diode is reverse bias and there's no feedback here. There's no feedback. No feedback, and therefore V0 will be equal to 0. Is this clear to all of you? Now, if we have to plot a characteristic V0 versus Vi, so how do you think it look? So now this is y-axis, okay? And then this is x-axis. So now if I have to plot V0 versus Vi, this is Vi and this is V0, right? So now if I have to plot V0 versus Vi, how does it look? So as Vi is increasing here towards the positive, V0 will also increase the same magnitude. This will have a slope of 1 basically, right? But when Vi is equal to 0, then V out will also be equal to 0. So when Vi is equal to 0, V out will also be, sorry, when Vi is equal to negative, this is when Vi is negative. So this will be when Vi is negative. So this will be 0 and this will be when Vi is positive. So when Vi is positive, V0 will follow Vi, therefore this will have a slope of 1. When Vi is negative, the output voltage will be 0. So this is a half wave rectifier basically. So this is a precision half wave rectifier. The circuit that we just saw is a precision half wave rectifier. Let me repeat. So the basic disadvantage of this circuit is when the input Vn is negative, you see that the op-amp here is going into saturation, right? So whenever the op-amp goes into saturation, for it to come out of the saturation and behave like an amplifier takes time. So basically this is going to limit your frequency of operation. So therefore what we'll do next, we are going to discuss a circuit wherein the op-amp never goes into saturation. So the circuit that we are going to discuss here is still a half wave rectifier itself, but then we are going to make sure that the circuit is never going into saturation. This circuit is similar to an inverting amplifier. Okay, let me call this as R. So this will be Vi. So when I say inverting amplifier, then I'll have a feedback resistance, which I name it as R here. But then we'll use 2 extra diodes here for rectification. Okay, so one here and another one here. Okay, so now this will be V0. So let me call this as diode D2 and let me call this as diode D1. So now let's see what happens when Vn is positive and Vn is negative. Okay. So when Vin is positive, when Vi, okay, so this is actually grounded, right? So this is an amplifier. This should be grounded. Okay. So now what happens when Vi is positive? So when Vi is positive, so the output, let me call this as Vx. Vx will be negative, right? Because the input is given to the inverting terminal. So therefore, when Vi is positive, Vx is negative. Since this is negative, the diode D1 here is reverse biased, right? So the diode D1 here is reverse biased, and there'll be no current through R because diode D2 is forward biased. So then the circuit will look something like this. For Vn is equal to positive, so this circuit will look something like this. So the diode D2, D1 is reverse biased, whereas this will look like a short. This will look like a short, right? So now Vx, when Vi is positive, when this is positive, this Vx will be negative, correct? So now, since this is a short, all the current flows here. So there'll be no current flowing through this path. That is, no current flows through R. So therefore, the output voltage V naught here in this case will be equal to 0. So this will act like a virtual short, right? This is also at 0 volts. This is also at 0 volts, correct? Since there is no current flowing through R, then V naught is also equal to 0 volts. So that is when Vi is positive, D1 is off, D2 is on, and V naught is equal to 0 because I through the R, that is the feed, that is in the feedback path is equal to 0. Is this clear? So when Vi is positive, V naught is equal to 0. So now let's take a look at the next case. So the next case is when Vi is negative. So the next case is when Vi is negative. So when Vi is negative, what happens to this diode D2? D2 will be reverse biased, correct? D1 will be forward biased. So this is going to be forward biased, right? So this will be when Vi is equal to negative, the voltage Vx will be positive. So therefore diode D1 is forward biased, diode D2 is reverse biased. So now you can see that this behaves like an inverting amplifier. So what's the gain of the inverting amplifier? V naught is equal to minus feedback R by the input R into Vin, right? So that's nothing but V naught is equal to minus Vin. Since Vin here itself is negative, you get V naught rectified. That is, you get a positive value of V naught, right? So therefore, in this case, when Vi is equal to negative, the diode D1 is on, the diode D2 is off, and V naught is equal to rectified Vi. So Vi is negative, but you get a positive Vi at the output. So you can see here at any point of time, there is a feedback path, either through the diode or through the resistor. and therefore this op amp is not entering into saturation at any point of time. Is this clear? The transfer characteristic graph for this. So we'll have to draw V naught versus Vi, right? This V naught versus Vi. So this will be Vi. This will be Vi. And this will be V naught. Okay. So what happens when Vi is positive? When Vi is positive, V naught is equal to 0. Right? When Vi is positive, V naught is equal to 0. When Vi is negative, so then V naught is positive with the same magnitude. Right? So this will have a slope equal to 1. So this is this portion. This portion is for Vi positive, and this portion is for Vi negative, and then this is 0. So we have learned now two half-wave precision rectifiers, where the first one rectifies, but then we see that at some point the op amp is going into saturation and we need to avoid that. Therefore, we come up with another circuit which looks more or less like an inverting amplifier with two diodes. Here we see that Vi, even if it's positive or negative, at no point the op amp is going into saturation. It's always behaving like an amplifier. Okay, so the next circuit that we are going to study is a full wave rectifier. Okay, I just have the circuit ready so that I do not have to spend some time drawing it here. So this circuit that you see here is a precision full wave rectifier. Okay, so this is a precision full wave rectifier. Now let's see how this works. Okay, so how is this built basically? So this requires two op amps. Okay, so one op amp is connected as a voltage follower with a diode in between. There's nothing but is similar to the super diode, right? So now another op amp is having a inverting, is behaving like an inverting amplifier. Right, so one is a voltage follower and the other one is an inverting amplifier. So basically you're giving the same input to both. So now let's see how this works. Now what happens when Vn is positive? So when Vn is positive, the output here, so let me call this as Vx. Let me call this as Vx. Okay, and let me call this as Vy. Vy, right? So here Vx is positive, therefore this diode is forward biased, right? So now when Vn is positive, okay, when Vn is positive, the diode D2 is forward biased, correct? So the diode D2 is forward biased. Therefore, let me short it. Okay, what happens to the diode D1? So Vn is positive. So this is given as an input to the inverting terminal. So therefore, the output here will be negative, right? The output at Vy will be negative. So what will happen to this diode? Basically, this will be reverse biased. The diode D1 will be reverse biased. This is how the circuit will look like now, right? When Vn is positive, the diode D2 is forward biased and the diode D1 is reverse biased. Why is the diode D2 forward biased? Because when Vin is positive, this is given as the input to a non-inverting terminal here, and therefore the output here will be positive. So the diode D2 is forward biased. When Vn is positive, the input here is given to the non-inverting terminal. So this Vy will be negative. Therefore, the diode D2, D1 here will be reverse biased. So now, since this has a feedback and this is working as an voltage follower, the concept of virtual short holds good here, and therefore this output here, due to the concept of virtual short, the voltage here will also be equal to Vi, right? This will also be equal to Vi. Because the input is Vi, the concept of virtual short holds good. Therefore, the voltage here will also be equal to Vi, which means V out here will also be equal to Vi. But let's see now what is happening to this part. Now, since this is also Vi and the output is also Vi, since these two voltages are same, there will be no current flowing through these resistors and this will remain at Vi. Do you get it? So when Vn is positive, let's just write it down here. So when Vin is positive, what happens? Diode D2 is forward biased. Diode D1 is reverse biased. And now the first amplifier, let me call this A1 and let me call this A2. So A1 behaves like a voltage follower and A2, it becomes open circuited and therefore this enters saturation. A2 enters saturation, right? And since A1 is behaving like an voltage follower, due to the concept of virtual short, now you will have V0 is equal to Vi. So when when input is positive, the output simply follows the input voltage. Is this clear? So now let's see what happens when the input is negative. So I'll just copy and paste it here so that we'll analyze. Yeah. Okay. So what happens? Let's see what happens when the input is negative. When the input is negative, then this will also be negative. So what happens to the diode D2? It will behave like an open circuit, and the diode D1 here will behave like a short. Why will the diode D1 be shorted? Because input is negative and that is given to an inverting terminal. So therefore Vy will be positive. So therefore this diode will be forward biased. Clear? So now what happens? So when Vi is negative, so now you do not have a feedback path here at all. This is open, right? So therefore you will have no voltage due to this. This is entered into saturation now. A1 has entered into saturation. Now let's see how this is behaving. So you have the input given to an inverting terminal and you have both the input resistor and output resistor equal to R and R. Therefore I can write V0 is equal to minus R by R into Vi, and therefore V0 is equal to minus Vin. Since Vin itself is negative, V0 is positive, right? So what happens here? So first, when Vin is negative, the diode D2 is reverse biased, correct? The diode D1 is forward biased, okay? And then amplifier A1 is open circuited I mean the feedback path is open. Now an amplifier A2 behaves like an inverting amplifier with gain equal to 1. With gain equal to 1. In fact, magnitude of the gain is 1, but then since it's inverting, you have an inverted output. Now, therefore, V0 is equal to minus Vi. Since Vi itself is negative, V0 is always positive, right? So now if I have to plot the output transfer characteristic of it, this is how it will look. So this is my XY axis, okay, where here I have my input Vi. Here I have my output V0. So now if I have to plot the characteristic, then when Vi is positive, V0 simply follows Vin, right? This will have a slope of 1. And now when Vi is negative also, V0 will be equal to minus Vi, which is positive. This will also have a slope of 1. So this will be when Vi is negative, sorry, positive. So this is the main circuit. This is the main circuit. Okay. So this is the reduced circuit when Vn is positive, where diode D2 is forward biased and D1 is reverse biased. This is acting like an voltage follower, and due to virtual short, you will have the voltage at this point equal to Vi, and that is appearing at the output. So V0 will simply follow Vi. So when Vn is negative, so here you have an open circuit and here you have a closed circuit. Now this is open circuited and therefore this enters saturation, while Vi is negative. This will behave like an inverting amplifier, inverting the negative input. Therefore, V0 is equal to minus Vn. Since Vn itself is negative, you get a V0 is equal to a positive value. That is a rectified output. Okay, so we'll go on to the next circuit now. So the next circuit is basically to make sure that none of the op-amps enter into saturation. It's again a precision full wave rectifier. So this is the circuit. And this circuit also rectifies, I mean, it's a full wave rectifier. But here we make sure that at any point of time, we do not allow any op-amp to enter into saturation. Okay. So now let's see how this works. First, when the input Vn is positive, so when the input Vn is positive, since you're giving it to the inverting terminal, V1 here will be negative, right? So therefore, here at this point, diode D1 is forward biased and the diode D2 is reverse biased. Diode D1 is forward biased and diode D2 here is reverse biased. So now let's draw this with the diodes forward and reverse biased. So when Vn is positive, okay, so this is negative, V1 is negative. So therefore, this diode is forward biased. The other diode here is reverse biased. So now you can see that this is behaving like an inverting amplifier, right? This amplifier here is behaving like an inverting amplifier with the magnitude of gain equal to 1, right? So let me just highlight this. Now this is behaving like an inverting amplifier with the magnitude of gain equal to 1. Therefore, I can write V1 Therefore, I can write V1 here is equal to minus V in. Correct? So that is the voltage at this point, V1 here is nothing but equal to minus V in. Now you can see that this is given as the input to the next inverting amplifier. This is also an inverting amplifier because here the input is given to the negative terminal, that's to the inverting terminal. So now here, this part of it now behaves like another inverting amplifier with an input voltage of minus VA. Here the input voltage here will now be equal to minus VA, correct? So the voltage here will be equal to minus VN. So this will behave like an inverting amplifier with an input equal to minus VN. Since both the resistors are equal, you can see here that the magnitude of gain is again equal to 1. Since this is an inverting amplifier, you will now have V naught equal to inversion of Vn, which is nothing but Vn. Right? This is when Vn is positive. So basically, when Vn is positive, you can look at the circuit as two inverting amplifiers cascaded, where both the amplifiers has a gain of magnitude 1, and each inverting amplifier here inverts the input. So therefore, the output will be positive. So V naught simply follows V in when V in is positive. So when V in is positive, the diode D1 is forward biased, the diode D2 is reverse biased. So now both the amplifiers here, let me call this as A1 and let me call this as A2. So both the amplifiers A1 and A2 here behave as inverting amplifiers with the magnitude of gain equal to 1. So therefore, V naught will simply follow the input. Now what happens to this path? There is another path here, right? There's another path here. Now what happens to this path? Can anyone tell me? So now this is behaving like an inverting amplifier. So the voltage here will be at 0 volts because it's virtual ground. And there is no current that can take this path because the input impedance of the op-amp is infinite. So therefore, that there cannot be any current flowing through R. So therefore, this voltage will also be at 0 volts. And that is why the second op-amp is also behaving like an inverting amplifier. So this is at 0 volts, and due to virtual short, this will also be at 0. It's a virtual short, correct? And that's why this is also behaving like an inverting amplifier. Is this clear? So I'll give you some time. Please make a note of it. And then we'll analyze what happens when Vn is negative and then close the session. Is this clear? Do you want me to go through this again? Is this clear? Shall we proceed? Is this clear so far? Okay, so we'll proceed. So now we'll have to see what happens. Please concentrate here. This is a little tricky. We'll have to see now what happens when the input is negative, right? So when the input is negative, the diode D1 is reverse biased, correct? Why? Because the input is negative given to the inverting terminal. So therefore, this is at positive, which forward biases the diode D2 and reverse biases the diode D1. So now this will form an open circuit and this will form a closed circuit. So now this will form a closed circuit. So let's call that voltage equal to V2. Okay. So now let's say the input current here is I. So at this point, it splits into two, right? So this will be I1 and this will be I2. And therefore, I can write here I is equal to I1 plus I2. Correct? So now, let's say the voltage at this point is V2 and V2 is given as an input to the non-inverting terminal here, and there is a feedback path here. Do you see there's a negative feedback path here? So this is again behaving like an amplifier with an input V2. So therefore, with the concept of virtual short, I can write the voltage here at this point is also equal to V2. Correct? So now this is also behaving like an amplifier because it has a feedback at the inverting terminal. You can see this feedback, right? It has a feedback path at the inverting terminal and therefore this is also behaving like an amplifier. Since this is at 0, since this terminal is at 0, this is also at 0 due to virtual short. I repeat. Now, let's say the voltage at this point here is equal to V2. Since the voltage here is V2, this is given to the positive terminal. And for this op-amp, you can say that it has a negative feedback. That is, it has a feedback connected to the inverting terminal. Therefore, this is behaving like an amplifier. And due to virtual short, the voltage here is also at V2. The voltages at these 2 points are same, right? If it's behaving like an amplifier. So therefore, I can say the voltage at this point is also equal to V2. Similarly, now this is also behaving like an amplifier because you have a feedback which is connected to the inverting terminal. And therefore, the concept of virtual short holds good here as well. So this is at 0. The voltage here is at 0 volts. Now, I can write I1 as V in minus 0 by R. That is I can write it as V in minus 0 divided by R. I1, which is the current through this, can be written as 0 minus V2 divided by R. So, which is minus V2 by R. Okay. What is I2? I2 is again 0 minus V2 divided by 2R. Right? I2 is 0 minus V2 divided by 2R. So therefore, this will be minus V2 by 2R, right? So this, if I simplify, I get Vn to be equal to minus 2 by 3. Sorry, I get Vn to be equal to minus 3 by 2 minus 3 by 2 V2, or I can write V2 is equal to minus 2 by 3 Vn. Is this clear to all of you? I've just tried to express V2 in terms of Vn by applying KCL at this point. Now, you can see here that V2 is given as the input to the non-inverting terminal, and then you have a feedback to this amplifier, right? So this looks something like that. Now you have an op-amp where the input given here is V2, and then you have a feedback here which is R, and here you have another R plus R which is going to 0 volts. So I can write this something. So here you have 2R which is going to 0 volts. So this looks like a non-inverting amplifier. That's basically this portion. Okay, I think, let me just mark it, okay? So it's basically this portion, okay? This is behaving like a non-inverting amplifier with a feedback resistance equal to R, and this resistance equal to R plus R to R going to ground. So now this is my V naught, right? So now this will be my V naught. Therefore, since it's a non-inverting amplifier, I can write V naught is equal to 1 plus R by 2R into V2, where V naught is equal to 3 by 2 times V2, but V2 is minus 2 by 3 times Vn, correct? V2 is minus 2 by 3 times Vn. Therefore, V naught will be equal to minus Vn when Vn is negative. Is this clear? V naught will be equal to minus Vn when Vn is negative, and therefore you get the rectified output. So we just go through this again. I just take a couple of more minutes. You guys came late. So when Vn is negative, what happens is the output voltage here will be positive, which forward biases the diode here, and the reverse biases the diode here. So therefore, now at this point, I'll try to apply a KCL here and try to find out what is V2 in terms of Vn. So if there's a current I flowing here, then this splits into two currents, I1 and I2. So I can write I is equal to I1 plus I2. So in order to find out I2, I need some voltage at this point. So as I can see here, V2 is given as the input to this amplifier. And then this amplifier also has a negative feedback. Therefore, this is behaving like an amplifier, not like a switch. So therefore, this voltage here is also equal to V2, right? So now I can write Vn by R, that is this current, is equal to minus V2 by R plus of minus V2 by 2R. So when I solve it, I get Vn is equal to minus 3 by 2 V2, or V2 is equal to minus 2 by 3 Vn. Okay. So now I'll have to analyze the second part of this, that is as in the second amplifier. So the input to the second amplifier here is V2, right? So this is, since this is a non-inverting amplifier, the concept of virtual short holds good. Therefore, this is also V2. And then from V2, you have R plus R, which is going to a virtual ground, which is at 0 volts. So if I redraw the second amplifier, it will look something like this. So this has an input of V2 with feedback resistor R and the other resistor 2R. Therefore, I write the gain equation V0 is equal to 1 plus R by 2R into V2. So when I solve this and substitute for V2 in terms of Vin, I end up getting V0 is equal to minus Vin. So therefore, since Vn is negative, you get a rectified output, and the output characteristic of this is similar to that of the previous one. It looks the same, right? This is a full wave rectifier, and the output characteristic will look the same as that of this. So basically here you are making sure that none of the amplifiers are going into saturation during the entire operation. As in, when Vn is positive or negative, none of the op-amps are going into saturation.